Okay, so last time we talked about using generative adversarial network or GANs to generate a synthetic patient records, or more likely tabular data, because it could be any data. It could be so as long as your target data has a structure where the rows are individual samples, which is in our case individual patients, and then columns are features, and in our case columns could be like individual diagnosis codes or medication codes or procedure codes. So that was our target. That was our aim, which is to generate the tabular data. And in order to do that, we needed to have a different technology, or like we needed to employ a rather different technique to guarantee that we don't fall into the mode collapse. So mode collapse, which is when your generator has figured out a way to win the game, which is the adversarial game, where it needs to trick the discriminator. So mode collapse is when the generator has found a way to trick the discriminator by generating a very small number of very realistic samples. So for example, if your GAN generates always the same image, which is realistic, of course. So if your generator generates the same image over and over again just to trick the discriminator, then that's when you say that your generator has fallen into a mode collapse. And the same thing can happen for MedGAN, for generating tabular data. So in order to avoid that, what I suggested is a technique called mini batch averaging. So just to recap, if your generator has fallen into a mode collapse, then your mini batch average, or the mean value of your mini batch, would look like this. Where the occurrence probability, if we're talking about binary data, if your occurrence probability would look like this. It's like either extreme. It's always 0 or it's always 1, or something like that. It's very dichotomized. So if you provide this information along with the actual synthetic data to the discriminator, then it would be very easy for the discriminator to distinguish whether the given mini batch of samples are synthetic ones or real ones. So in order to win the game, the generator needs to generate a more varied data, more diverse samples, diverse set of samples. So that's one way to avoid mode collapse. And when you're, this is another story, but when you're generating images, there was something else called mini batch. I forgot something. It was proposed in the very early days, like in 2016 or something, how to generate more varied images. It was called mini batch something, but basically it was to like encourage generator to generate more diversely distributed images. So the philosophy is the same. It's like you want your mini batch of samples to be more diverse, and in our case, in MedGAN, you do that. You encourage that by simply providing to the discriminator the mini batch average, which is very intuitive, because if we're talking about binary data, then it's either something happens or it doesn't. And if you calculate the mean occurrence probability per column, then it's very intuitive what that means. And if we're talking about count data, like how many times some feature happened over time, if we're talking about count data, then if you do mini batch averaging, then your individual column, the value that would be inside here would indicate the average number of times that feature happened in your data. So that will still be very intuitive. So in the experiment section, we will see how much this helps. This mini batch averaging technique helps when the MedGAN generates synthetic tabular data. By the way, is there any question from the last time, like any question that's generally applicable to GAN architecture, or specifically to MedGAN, or the technique about, I mean, question about the technique in mini-batch averaging, like any question. Nope. Oh, one more person came. Let me see. Oh, okay. So, all right, I guess we have all the usual attendants. Right, okay. All right, moving on. So basically GAN architecture with autoencoder, with a pre-trained autoencoder plugged in. I mean, only the decoder part, but pre-trained decoder plugged in on top of the generator, and then generator having like batch norms and residual connections, then using mini batch average. So that would be the entire summary of the MedGAN architecture. So we have the architecture, then we need to have an experiment. So what I did is use 3 sets of data sets. So there's something called Sutter PAMF, which is borrowed from the, oh, sorry about that, which is borrowed from a healthcare network called Sutter Health, which is a California-based healthcare network. And they gave me about 260,000 patient records of 260,000 patients. So that is the entire data set, Sutter PAMF. And a subset of them, a subset of Sutter PAMF is called Sutter Heart Failure, which is Sutter HF. So among 260,000 patients, there are 30,000 patients, subset of the patients who qualify as a training set for heart failure prediction. So not all people qualify as heart failure prediction training sample. Like you need to be in a certain condition, like certain age, certain gender, certain number of times you've visited the hospital, certain like diagnosis or medications that you've taken. So you need to have certain characteristic to be qualified as being a member of the training sample for a heart failure classifier. Anyway, so Sutter HF is a Sutter PAMF subset, and then of course there's MIMIC3, which all of us are very familiar with. So about 50,000 a number of patients, and I've grouped the codes. So what I'm generating here is basically diagnosis, medication, procedure codes. And the number of codes are obviously way smaller than the actual number of data, the actual number of codes, because I've grouped them into like smaller, like higher concept basically. So like all the 5-digit IC9 codes, I converted them to 3 digits or something along the line, like that. It's not exactly that, but something along that line. Right, so. There are some, these days it's called ablation studies. So like with the same architecture, I just add more functionalities from the basic GAN to add something, and then I add autoencoder, the pre-trained autoencoder. Then again, I add the mini batch averaging, and then I add the residual connection and batch norm to the generator. Oh, here it is, mini batch discrimination. So mini batch discrimination is it was a technique proposed for generating diverse images by Tim Salimans. So that was the first technique that was introduced in the image domain for GAN for GANs basically. So if you use this, then I mean empirically they claim that if you use mini batch discrimination, then your generator generates more varied images. But in the tabular data case, it doesn't work very well. Like mini batch averaging is way better than mini batch discrimination. But I'll show that empirically. All right. So ablation study. So there's just simple GAN. There's pre-trained autoencoder GAN. There's like 2 types of different mini batch, 2 types of techniques to avoid mode collapse. And then there's the final version, which is adding the residual connection to the generator. And then there are, of course, we need other baseline models other than the MedGAN itself. So one is random noise. So random noise means that you have the real data, and then so basically I'm talking about binary data. So you have a real data of binary tabular data, and sometimes you randomly flip some column from like 0 to 1 and 1 to 0, like you just reverse it with probability 1.0. So by 10% chance, you take one cell or one column in your sample, and then you reverse the value. So that's basically injecting noise to guarantee privacy, basically. So, if you do that, then if you randomly flip an actual number, like reverse it, then you're destroying the distribution of the true data. So it's a trade-off between guaranteeing privacy and actually, maybe degrading the quality of the data. And then there's independent sampling, so which means that this is tabular data. So you can just calculate the mean occurrence probability of each column, which is basically what I do in mini batch averaging. But you can do it beforehand. You can do it before you actually train the data, train the MedGAN. So you take the real samples, which could be the Sutter PEMF or Mimic3 or Sutter HF. You just take the real sample, binarize it, and then you calculate the mean occurrence probability for each feature. Like the first feature has 0.5 probability. Like the second feature is like 0.20, like 25%. Maybe third column has like 76%, something like that. And then the mean occurrence probability, and then you just sample it independently. So if some column has 76% chance of occurring, then you just sample it with that Bernoulli sample it with that probability. So it's independent sampling. So it doesn't guarantee a correlation between like a set of columns or the underlying relationship between like several columns. It's just independently per column, you're sampling the value. So on the surface, it would look okay, of course, because you're sampling per the actual occurrence probability. But if you dig deeper, it wouldn't make sense, because you're destroying the correlation, the relationship between like number of columns. All right, and then we have stacked RBM, which is restricted Boltzmann machine, which is a very old machine. So RBMs are like old techniques that people don't use these days anymore, but that was like the savior for neural networks. One of the few cases where multiple stacked layers worked. So that was like if you stack restricted Boltzmann machines, like 5 stacks, 6 stacks, or 7 layers, and then you train it with a very specific technique, then it would actually increase performance. And that was very old days. It was like back in, I don't know, like maybe 2011, 2009, something like that. And it's a generative model. RBMs are generative models, and especially for count data. Especially for binary data. So if your data consists of zeros and ones, then you can train restricted Boltzmann machines to generate new data by sampling using something called I forgot, a Gibbs sampler. I'm sorry. Yeah, Gibbs sampler. Sorry about that. Yeah. Anyway, so that's stacked RBM, and then variational autoencoder is also I guess a lot of people have already heard about it. VAEs, so variational autoencoder. So it came out in about the same time as GANs, with a very different philosophy. I won't go into detail what VAEs are, but it's just it's a more probability. It's a more principled technique that is grounded in probability theory to generate synthetic data. So like GANs generate data out of nowhere. As I said, generators take a normally distributed noise and then convert that to actual real like synthetic samples. So there's no good way to explain the relationship between random noise to the synthetic data. But in VAEs, in variational autoencoders, what you enforce or what you encourage the model to do is the model takes a normally distributed data and then I mean, you still sample from normal distribution, a noise, and then map it to synthetic data. But in by doing so, by training VAEs, you're actually learning a space, learning a like a hypothetical space where where real samples are normally distributed, like your like MNIST images, like 1, 2, 3, 4, 5, 6, 7, 9, 9, 10, like 9, like your digits are normally distributed in a like a latent space. So it's more principled than GANs, but also there's like a trade-off. So VAEs are more principled, but their outputs are to human eyes, their synthetic samples have like lower quality. Like their images are not sharp enough. It's more like blurry. And GAN images are way sharper, like way more likable to human eyes. And deep fake these days, like the pornography, the deep fake, it's all GAN based basically. That's like the clearly shows which architecture, which approach guarantees more high quality output. GAN versus VAE. It's GANs always. Anyway, so that's a bit of a side story. Anyway, so baselines are random noise independent sampling, stacked RBM, variational autoencoder. I mean, it was basically back in like 2017 or like late 2016. So there weren't a lot of baselines to compare with, basically. All right, so quantitative evaluation. So as I said, there are two objectives that you need to achieve when you're generating synthetic medical records. One is the quality of the outcome, and another is the privacy. So quality of the outcome. So it's kind of difficult to guarantee the quality of your synthetic data because we're talking about data that is synthetic, which is not real. So there's no good way to measure how real it is because we're talking about something that is fake. So so I came up with a couple of evaluation techniques or strategy, so to speak. So given the synthetic data, I mean, given a set of synthetic samples, what's the good way to quantitatively evaluate its quality? How real are they? Like how real are my synthetically generated samples? So one is dimension-wise probability. So it's just a independent sanity check, basically. So you take per column, you just take one column at a time and then just calculate the occurrence probability. Like you do it for the real samples, like the real set of samples, and you do it for the fake set of fake samples or synthetic samples, and then you calculate the mean occurrence probability and just basically compare it. Like for the first column in the real data, it had maybe like 36% occurrence probability, and you take the first column of your fake samples and calculate, and if it has the same 36% chance of occurring, then it means that at least on the surface, your fake samples has learned the occurrence probability. But again, as I said, this is just sanity check. So it's a very, very basic technique. And just because your synthetic samples have the same dimension-wise probability doesn't mean that it has captured the underlying relationship between multiple columns, right? Yeah, there's no guarantee. It's just, yeah. So when we're doing dimension-wise probability check, like the sanity check, then the independent sampling technique would always, perform very nice, like show a very good performance. But again, as I said, doesn't guarantee that it is the best. Doesn't guarantee that your fake sample is capturing the relationship between like at least two columns or 3 columns or 4 columns. All right, so that's the first evaluation technique, and the second is dimension-wise prediction. So this is more advanced, more difficult. So this is what is called a train with synthetic and test with real. So you've generated like a bunch of set of fake samples and you have a bunch of real samples. So in the real samples, you split it with training and test samples, like you would split, like maybe 80-20, maybe, or 90-10. You just leave something off as a test sample, and then you train your classifier. Basically, you train your classifier to predict given, like, for example, let's say you have 100 columns or 100 features, then you take 99 features and then try to predict whether the remaining feature is 0 or 1. So that's basically like leave one off feature. So again, so you take all the features you have except one particular column, and then using the other columns, you try to predict that specific column, and you train it with your training portion of the real data, and you train it with your synthetic data. And then once you've trained your classifier, you test it on the real sample, the one that you've left off, one that you just left behind as a test sample. So by doing so, if you're classifying, so there are two sets of classifiers basically, one that is trained on the real data set, one that is trained on the synthetic ones, and then you test both classifiers on the real samples, the one that is left off. And if both classifiers show similar performance, then that means that your synthetic data is at least capturing some relationship between multiple columns. So that this is a way more complicated task than dimension-wise probability, right? So, and then you can repeat this process with each and every single feature. Like you take first feature as a target, as a prediction target, and then you use the old remaining ones as a predictor variables or features. You train classifier, and then that is one way. I mean, that is one iteration, and then you move on to the next feature, like column number 2. You pick that as the target variable, like the prediction target. So you take that as a label, and then use the remaining columns as the features, and you train 2 classifiers again and again and again and again. So mathematically speaking, if you have 100 features, then you can train 100 different classifiers predicting each and every column, and then you have like 100 outcomes to evaluate basically, right? And so the classifier that we're training to predict a specific particular column is logistic regression. So it's a very basic classifier, right? So okay, so this task, all tasks are experimented on the Sutter PEMF, and so let's move on to the dimension-wise. So the first, as I said, first is dimension-wise probability. Second is dimension-wise prediction. So dimension-wise probability, and again, I'm saying I need to specify that this is for binary tabular data, not the count tabular data. There are results for count data, but again, but for the as in the first, I'm going to talk about binary data, which is way easier to explain. So I've binarized all the data in the Sutter PEMF, which is the larger one, which consists of patient records of 260,000 patients. So I took that, and then I've generated a bunch of about the same number of 260,000 samples of synthetic ones, and then I'm evaluating the dimension-wise probability, the independent column-wise or feature-wise occurrence probability. And the first row is the ablation study, all the different MedGAN variants, and the second row is the MedGAN versus the baselines. And the more realistic your synthetic samples are, so the more the dimension-wise occurrence probability, the more similar they are to the real ones, then the dots will align along the diagonal axis. So because what is happening here is this one, no, I forgot. Okay, so this axis is the the occurrence probability from the real data, because not all columns, not all features would have the same occurrence probability. Some feature would have like 10% chance of occurring. Some column would have like 99% chance of occurring. Like some other column is like 70%, 75% chance of occurring. So not all, we take the individual, like each column, and calculate the mean the occurrence probability, and then plot it on the x-axis. And the y-axis is the occurrence probability calculated from the synthetic data set, synthetic ones, the ones that are generated from the MedGAN. So not all features would, so even the same feature, the same like column, the corresponding column might have a different occurrence probability. For example, here, like this specific dot here. So this means that from the real samples, this dot has about 75% chance of occurring. But in the synthetic ones, this column has only 30% chance of occurring. So which means that it is a very low quality synthetic data set. It's not so real because they don't align. Like if we're talking about the same feature, same column, then it should have the same occurrence probability. Like if from the real data, this column is 70% chance of occurring, then from the synthetic ones, it should also have the 70% chance occurring. So which would be placed in the diagonal line here. So that's why I'm saying that the more the dots are aligned on the diagonal line, then the more realistic they are, the synthetic ones. So so obviously, just training your very simple GAN without any techniques, without any like modifications, no autoencoder, whatever, it doesn't work very well. Because so this is just simple GAN trying to generate tabular data, binary tabular data, and you can see it doesn't align well on the diagonal line. And then if you add a pre-trained autoencoder, I mean, you pre-train an autoencoder and you take the decoder out of it and then plug it on top of the generator. Qualitatively, it looks a bit better than just vanilla GAN. And then after that, you add the mini batch averaging, which is this. So mini batch averaging. So a jump from here to here is dramatic. So just by using mini batch averaging, at least the dimension-wise probability, like to our eyes, it's way better. It's way more aligned on the diagonal line compared to this one. And if you use mini batch discrimination, which was proposed in the image domain, it doesn't work very well. Like compared to this, mini batch averaging, mini batch discrimination doesn't work very well. So yeah, it's not a good idea to use techniques that are developed for specifically developed for images. It's not going to work on tabular data. And then after this, if you add the batch norm and residual connections to your generator, it becomes like almost as good as the diagonal line itself. So dimensional wise probability compared like if you add more like techniques, then the final form, the MedGAN, looks very, very real, at least in the sense of dimension-wise probability, the mean occurrence probability. Okay, then comparing to the baselines. The random noise. So random noise is basically, it's just skewing the distribution because you're by using like on 10% chance, you are flipping, you're reversing the 0 to 1 and 1 to 0. So it might look okay, but it's not exactly moving along the diagonal line because there's like a small shift because you're like reversing the values 0 to 1 and 1 to 0. You're basically tilting the actual distribution. So that is why the line is a bit more skewed than the actual diagonal line, but still it looks okay. And then this is independent sampling. So independent sampling should like perfectly achieve this, like perfectly win this game, win this dimension-wise probability, because independent sampling was generated according to dimension-wise probability. So it should, of course, win this game. It should be perfectly aligned. But again, as I said, doesn't guarantee that it has captured the underlying relationship between columns, between features. But on the surface, it looks good. Okay, so this is stacked multi-layer restricted Boltzmann machines was back in the days called deep belief networks. I don't know why, but it was called DBN. So okay, so it looks okay. Looks pretty aligned on the along the diagonal lines. VAEs, it's way better than like GANs without the batch norms, or GANs without the mini batch averaging, but still it's not as good as the GANs or DBNs, but it's not too bad either. All right. So moving on to the dimension-wise prediction. So that, again, this is like when you train two separate sets of classifiers to predict just a single column based on all the other columns. And then, so the caveat is, even if you use the real data to train your classifier to predict a specific column, doesn't guarantee that your classifier is like, classifier is perfectly performing that prediction, because first of all, we're using logistic regression, which is not a very powerful model compared to like random forest, or these days like multi-layer perceptrons, or even like support vector machines. I mean, support vector, I'm sorry, forget about that. Anyway, so logistic regression is not a very powerful technique, but the fact that we're using that to train to predict a specific column, that means that at least when you're using the real data set to train your classifier, doesn't guarantee that it's perfectly performing that task. But at least we're playing a fair game. We're not using, so if you use logistic regression for real data set and you use random forest to train on the synthetic data set, and then comparing performances, that's a unfair game. But here, at least we're using both. In both cases, we're using logistic regression. So at least when they perform similarly, like the one trained on the real one trained on the real data set and one trained on the synthetic ones, if they perform similarly, then at least we can say that the synthetic ones show like some similar distributions as the real ones. Again, the dots here are like individual dots were recorded based on so let's say how to best put it. So if we have 100 features in your 100 columns in the tabular data, then there should be 100 dots basically, because you train a specific you train logistic regression for a specific column, specific feature, and the performance, the AUC, I think, is it the AUC? Oh, it's F1 score. Sorry about that. So you train a classifier, binary classifier for a specific column, train the real ones and train the synthetic ones, and then you can measure their performance on the unseen test samples, real test samples, and measure the F1 score, which is yeah, I'm not going to go into detail what F1 score is. This is something similar to procedure recall curve, area under the procedure recall curve, but basically you want to balance out the procedure recall. But anyway, you calculate the F1 score of the classifier that is trained on the real ones, and then you can calculate the F1 score of the logistic regression classifier trained on the synthetic ones, and then plot it. And again, in the same logic, the more aligned the dots are along the diagonal line, the more like the better the synthetic data set are capturing the distribution of the real data set, basically. All right. So again, ablation study tells us that basic GANs, the vanilla GANs, are not doing very well, because you can see that a lot of dots are here, like it's just attached to the bottom, which means that for the real data set, the classifier trained on the real data set, they have varying F1 score along this line. Like some are like 90%, like 0.9 F1 score, some are like 0.1 F1 score. But for the classifiers trained on the synthetic ones, for the same feature same target, they're all showing like zero F1 score. Basically, they're failing, obviously. And then if you use if you if you use a pre-trained decoder, then it is picking up a bit. So you unhumanized, it's a bit, it's at least like not, at least some of the dots that were like here sticking to the bottom, they are like kind of lifted. And then using mini batch discrimination, I don't think there's any qualitative changes. Here, if you use mini batch averaging, then you can see that not a lot, the dots that were like sticking to the bottom, at least some of them are like up here. It's not the same number of dots that are like sticking to the bottom, but still like significant portion are here. And then if you use MedGAN, then you can see that not a lot of dots are no longer like just sticking to the bottom. So you can see that clearly mini batch averaging helps. There's like a lot of change from here to here, and then again a lot of change from here to here. So giving more power to the generator helps again. So it's like way better than before. Like we started from here, and then we arrived at here. So comparing the two, it's a dramatic change. Like a lot of dots are moving along the diagonal lines. All right, so to compare to the baseline, so random noise seems to do well, but again, random noise is a very stupid way to generate synthetic ones, because you're just flipping the zeros and ones here. As suspected, independent sampling might win the previous game, just comparing the dimensional-wise occurrence probability. But here we're calculating the prediction probability for each columns based on all the other columns. So in order to win this game, you need to capture, your data set needs to capture the relationship between a specific column and all the other columns. So independent sampling is just terrible at this game. Now DBN is I think it's a close second, or maybe as good as the MedGAN. So you can see that qualitatively there's like there's only marginal difference between this and MedGAN. VAEs, it's better than, I guess it's almost as good as GAN with only the mini batch averaging, or maybe a bit better than that, but clearly not as good as DBNs or MedGANs, right? Okay, so this is the quantitative evaluation for the binary variable. And there are some couple more evaluations results from the count data. So this is dimensional-wise average count. So we're talking about count data, not binary data. So if you use dimension-wise, so the counterpart of dimension-wise occurrence probability is the dimension-wise average count. And yeah, so this time I didn't like compare with all the other like GAN variants, the ablation study, or independent sampling, or independent sampling or random noise. It's like, it's just more of a sanity check. So independence, of course I didn't do like DBNs, because restricted Boltzmann machines, they're models for they're binary models. Basically they're specifically designed to train with binary variable. I mean, you can make some modifications to Boltzmann machines to be able to adapt to like count data, but that's another story. So here there's only two baselines. One is VAE, because you can easily train VAEs to generate count data as well as binary data. So VAEs, and this is ISKD, which is independent sampling using kernel density estimator. Something more like more advanced than just simply generating binary variable. But this is, again, the thing to note is that this is independent column, like feet per column generation. So again, so even for count data, MedGAN is, it's moving along the diagonal lines. So it is way better than ISKD or VAEs. And of course, the count, when you're generating count data, you can draw a histogram per feature, like how many times like they occur in the actual data set and the real data set, and you can see that. So this is essential so we can take like specific diagnosis code, like essential hypertension, some disorder of lipid metabolism, connective tissue disease, skin disorder, cardiac dysrhythmia. You can take basically some, like randomly, you can just take some diagnosis code and then plot their histogram. And the first line is the histogram from the real data, and the second line is the histogram from the synthetic data. And you can see that the count, so like essential hypertension has a different count distribution compared to skin disorder. You can see that their distribution, their histogram looks different from the skin disorder. And it's the same for the synthetic ones. Like, I mean, for here, it's a bit it's not perfectly aligned, but at least the trend is moving along the same trend. Like this trend here is like almost perfectly reflected in the synthetic ones. Like here, the distribution change, like histogram difference between skin disorder and essential hypertension, there's a lot of difference between these two, even in the synthetic ones. So synthetic ones are like, I mean, the MedGAN, the architecture, it can adapt to both binary data and also for the count data. So it's a very robust architecture. I'll just skip this one. And yeah, this is, okay, so this was all like Sutter data set. It was either Sutter PAMF, Sutter heart failure. So we move on to a completely different data set, which is MIMIC3. And this is, I've binarized the MIMIC3 data set. And then, so this is dimensionalized probability, like per dimension, the occurrence probability, the mean occurrence probability. And you can see again, the ablation study shows that the MedGAN, all the techniques that I've used, like the mini batch averaging, the residual connections, they're all useful. And again, DBN, compared to the baselines, DBN is, again, maybe even a slightly better than MedGAN. VA is not so much. So DBN shows close, like very similar performance compared to MedGANs. But the problem is the DBNs can only, learn from the binary data. But as shown before, as shown like above, MedGAN can perfectly, not perfectly, but like very well learn the distribution of the count data as well. So it's a better generator for tabular data. I'm gonna skip this. All right, so the fun part. So this was, so far it was all quantitative evaluation. We're talking about dimension-wise probability and dimension-wise prediction, and we were just showing like a couple of examples from different data sets. But now we're talking about qualitative evaluation, because as I said, those like two evaluation strategies, the dimension-wise probability and dimension-wise prediction, they're just a approximation, like they're just a proxy for evaluating how real the synthetic ones are, because there's no way to perfectly tell like how real the synthetic data are. So another way to do it is to ask a expert, ask a medical expert to, just look at the data and see how real they look. So we just asked a fellow doctor, actual physician. And so what we did is we randomly sampled like 50 real data set, 50 real samples and 50 fake samples. And then we shuffled it. And then we gave that 100 samples to actual doctor and asked the doctor to, assign a score. Like if some sample looks real, the perfect score would be 10. And if some sample doesn't make sense, looks fake, then just like 1 is the lowest grade that he or she can give. So, all right, and there's a little caveat. We gave the data set that we gave is, first of all, it's binary, and second of all, oh no, is it count? Yeah, it's count. I'm sorry, it's not binary data. It's a count data set. So we trained MedGAN on the count data set and then generated synthetic ones. So it's a bit more difficult challenge than binary data, because intuitively it's easier to fake with binary data compared to faking with count variable. So, and but the caveat is we've grouped the variables into, again, we were using grouped features, so not like complete 5-digit IC9 codes. So it's like using 3-digit IC9 codes only. Anyway, so okay, so like 50 real ones, 50 say fake ones, randomly shuffled, and then score between 1 to 10. And you can see that the outcome, this is a box plot. So the samples from the reals and the samples from the fakes, they are scored about the same. They have about the same mean score. So the red bar is the actual mean. So almost all real samples were given the score of 7, and almost all fake samples, all 50 fake samples, were given the score of 7, well, maybe 6.9 or 7. And this is the probably this box is about, I think it's a 1-star deviation from the mean. So even the 1-star deviation is about the same. So like it's almost exactly the same distribution, like that, which means that to the eyes of the doctors, even using the count data, it's not really easy to tell between the real ones and the fake ones. So qualitatively, it's about the same. But there are 2 outliers. You see the plus sign here, which means that 2 specific samples were given the score of 2 and 1. And the reason is pretty interesting. So yeah, okay, so I think there were 2 cases. One is even more interesting than the other, but one is so like so the doctors know that if there are some medications that occur, then there always should be a following medication. I'm sorry, some diagnosis. So if the patient has some diagnosis or some symptom, basically like some, I don't know, maybe hypertension or whatever, then there should always be a following medication. But the fake ones were missing that. So the real ones did have that pair of diagnosis and medication that always go together, but in the fake ones, it was missing the medication part. So the doctor knew that this is definitely fake, because any doctor or any real data would have that corresponding medication that comes along with the specific diagnosis. So that was one cue. And another is even more interesting. Another is co-occurrence of male-related codes and female-related codes. So I don't know, it's like some disease that are specific to male patient and some disease that are specific to female patient, they were co-occurring in the same fake data, fake sample, the fake sample, like within the one single fake sample, there were 2 codes that were occurring to males only and females only. So that is definitely a wrong sign. That is like the cue, like they definitely cue for the doctor. So there were 2 outliers. And like these discovery of lack of suitable medication or co-occurrence of male-related codes and female, like these scenarios tell us that the MedGAN, the generator, has not perfectly learned the distribution of the features. Like if the generator has learned perfectly well the relationship between features or columns, then this kind of thing would never happen. Like co-occurrence of male-related, female-related, this would never happen if generator picked up, like has perfectly learned the distribution. So this means that there's still a lot of rooms for improvement with the MedGAN architecture. Maybe if we, like we talked about in the previous class, maybe if we use the like not just the mini batch averaging, not just the first order distribution, that means first order statistical information, but maybe if we use the second order statistical information, the correlation between like pair of features, this would not happen, at least. But that's another story. All right, so the final thing is, okay, we don't have a lot of time. How many? Yeah, there are. Okay, so maybe we can finish this today. All right, so the second thing. I'm sorry. All right, another axis that we need to cover is the privacy issue. I'm sorry. Yeah, So one was the quality of the synthetic ones. The other is like, are they actually preserving privacy? Because the motivation for MedGAN is we wanted to generate like an infinite number of fake samples so that like the healthcare researchers in the world would have like access to a lot of fake samples that has no privacy problems at all and still conduct high quality, like, you know, machine learning research or AI research. So, okay, so what, at least from the previous like quantitative qualitative evaluation, MedGAN seemed to work pretty well. But again, another question is, does it really preserve privacy? So in order to assess this, in order to evaluate privacy preservation performance, we use two techniques. Which is one, membership inference attack, and two is attribute disclosure. So one, the membership inference attack is exactly this. The attacker has complete knowledge of patient group P. Sorry. So the potential attacker, like the one who's actually trying to, you know, mine the to try to look at the fake samples and try to, you know, mine the privacy information from the fake samples to of the real samples. So there's an attacker. So the attacker observes the synthetic data set from the MedGAN, and the attacker can identify if anyone from the actual real one was in the training set. Training set mean like the ones that are used to train MedGAN, because you need in order to train MedGAN, you need a real set of samples. And if an attacker knows that there's a certain, like a specific patient that he or she, the attacker, knows, like, I know this person to be a patient or a real patient, it may be in the Sutter pen or whatever. And just by looking at MedGAN, just by looking at the synthetic samples generated from MedGAN, if that attacker can say that this patient that I know beforehand, this patient that I know was used to train MedGAN. If that attacker can say that, then there's a membership inference attack. And I mean, this is not a very like, you know, not a big problem, at least to my estimation, because in order for this to happen, the attacker needs to already know the identity of the patient. So this doesn't have a lot of value in real world. Like, if you already know the identity of the patient, then you might as well just use that information to begin with. Like, just you know, identifying whether some patient that I know, some individual that I know was used to train MedGAN is not a very interesting, not an interesting problem. But at least it's like a sanity check. Just, you know, just by looking at we wanted to see if MedGAN is simply copying the real samples, just to, you know, trick the discriminator, because that could also happen theoretically. So that's what membership inference attack is. An attribute disclosure is way more interesting than the first attack. So this is that we're assuming that the attacker has a partial knowledge of a specific patient. Like for example, like, I know patient like John is suffering from, I don't know, maybe hypertension or kidney disease or, you know, heart failure. And looking at the synthetic data set generated from the MedGAN, can the attacker fill in the knowledge, the lacking knowledge of the attacker who has, you know, like, lacking knowledge that the patient has on the specific patient X. Like, as I said, like, the attacker knows that at least patient John has heart failure, and then I want to see if patient, like, the rest of the information of the patient John, like, I know that this patient has like this specific set of symptoms, and I want to know the rest. I want to fill in the rest, like what kind of medication that patient is taking, what kind of other diagnosis the patient has gone through, and what kind of other procedures that the patient has received. Like, the remaining portion of the information, I want to fill in that portion by looking at the synthetic data set generated from MedGAN, because I know that MedGAN was trained on patient John. It's like something along that scenario. So this has way more value than before the membership inference attack, because like depending on how much I know, how much the attacker knows about the patient X, that can determine like how accurately that attacker can fill in the rest of the information. Right, so like this is attribute disclosure. So membership inference attack, I'm not gonna go into detail like how I did it, but the bottom line is, so the mean precision and sensitivity, so the varying R means, I'm sorry, so R is the complete, oh wait, R being not gonna hang this info. I'm sorry, synthetic. All right, yeah. So I'm basically splitting between like there's like, in order to identify, in order to perform membership inference, you need to like split the data set into like the ones that I know and the ones that are generated by the synthetic data set. And the more I know, the better the chance that I have of the more real patient that the more number of real patients that the attacker knows, there's a higher chance of probability. There's a higher chance of identifying whether the ones that I know are in the synthetic data set. I mean, were used to train the synthetic data set. Like, for example, if I know only one specific patient, like the complete knowledge of one particular patient, and trying to decide whether that patient was used to train MedGAN, it's a lot harder compared to the case where I know like 30,000 patients and trying to decide whether some patient that I know was used to train MedGAN. So there's like a bit of a, like theoretically there's a bit of a like difficult, it could change the difficulty of doing membership and inference attack. And the bottom line is it is the like it would be very bad for MedGAN if the more we generated synthetic ones, the more it's easy, the easier it is for the attacker to do membership inference. That would be terrible. Like, I mean, so intuitively, if you generated only like 10 fake patients, 10 synthetic records, it would be very hard for the attacker to see if the patient that he or she knows was used to train MedGAN based on only 10 synthetic samples. That would be very hard. But if MedGAN was a bad generator, it's just simply copying from its memory, then the more samples that the MedGAN generates, the easier it is for the attacker to perform membership inference. But just look at this line here. Just look at this line here, or any line basically. The more number of synthetic patients that we generate, like 5,000 synthetic ones, 10,000 synthetic patients, all the way to like 35,000 synthetic patients, the precision, the success probability of the attacker doing membership inference doesn't really change. So it doesn't really change. So that means that at least MedGAN is not simply copying from the real data. So yeah, I won't go into detail. I have some other things to discuss after this, actually, before I finish this lecture. All right, attribute disclosure. Again, I'll just jump into the conclusion. So as I said, the more attributes that the attacker knows, the higher chance of, the easier it is for the attacker to fill in the gap. Because, like, for example, if you know 90% of if you have 90% information about a specific patient, John, and then it's probably easier for the attacker to fill in the remaining 10, because you can just simply look at all the synthetic ones and try to match the synthetic samples that are as close as possible to the 90% information of John, right? And then you can just copy the rest. So anyway, so just the bottom line is, I think where was the bottom line? Right. So realistically, we're gonna assume that the patient knows maybe a 1 or 5% chance and 1 or 5% portion of the specification, like patient John, I know only 5%, like 5% information. I have only 5% information on John, and I want to fill in the rest of 95%, or maybe 10%, and I want to fill in the rest of the 90%, something like that. And realistically speaking, if you know only 1% or 5% or 10%, even 20%, there's a very, very low chance of filling in the gap by looking at the synthetic data set generated from MedGAN. So yeah, so which means that realistically speaking, just by using MedGAN, there's almost no there's no danger, no risk of membership inference attack. So again, because as I said, because MedGAN is not simply copying from the real samples, there's like very low chance of successful membership inference, which is to begin with not a very interesting problem. The more interesting problem, which is attribute disclosure, again, realistically speaking, you need to have a significant portion. You need to have like knowledge on significant portion of the patient to begin with, to fill in the rest of the knowledge, the rest of the portion of the patient, to reliably fill in that remaining portion. Otherwise, you won't be able to trust the portion that you filled in. As an attacker, you can't really trust the information that you filled in, because MedGAN is not simply copying from the actual data. So okay, so the bottom line, so the summary is quantitatively it generates high quality synthetic data, and MedGAN does not risk privacy. So attacker can confirm the presence of very small number of patients. So the membership inference it's only valid for very small number of patients. And I don't like, it's in reality, this is easily avoidable by just filtering out very old patients, or filtering out patients with really rare diseases, something like that. And attribute attacker cannot gain useful knowledge on unknown attributes. Like realistically speaking, statistically it's almost impossible. So that's the bottom line. So yeah, so that this type of research along the generation of synthetic tabular data is like still ongoing. It's not as popular as generating images, because it's not like generating images is way sexier than generating tabular data, because you can see it with your eyes, or at least generating audios is you can hear it with your ears. But generating tabular data, you need to quantitatively evaluate it. It's not as intuitive. So, but there are still some people that are very interested in this domain. Like usually it's the people from healthcare domain, actually. So like tabular GAN or T-GANs, or like table GANs. There's like follow-up works after MedGAN. And I think the most recent work is from last year in NIPS or something, T-GAN. Anyway, so yeah. All right, so this is the, okay, so this is the conclusion from all the MedGAN, yeah, the topic of MedGAN. So any question before I jump into the next discussion point? So any question or any like general curiosity regarding like generative models or synthetic data sets or GANs or VAEs or whatever, like any question, just, yeah, I'll wait for like several seconds.